Working memory has a fixed physical capacity. We can only hold a limited amount of information at once. This capacity represents a boundary in cognitive load theory. The container is strictly limited. Two specific loads fill this space. Intrinsic load is the difficulty of the material itself. Extraneous load is the mental effort required to process how that material is presented. Standard instructional design assumes that if formatting is poor, extraneous load increases until the container overflows and learning fails. However, research shows in some cases, high extraneous load from poor design has no negative impact on learning. The total load remains below the capacity limit. The effectiveness of instructional design depends on the intrinsic difficulty of the task. This relationship is defined by the element interactivity effect. Poor formatting becomes a problem only when the material requires high levels of mental processing. When the baseline load is low, the brain can manage the poorly designed presentation. Intrinsic cognitive load refers to mechanical interactivity, the degree to which essential pieces of information must be processed together to be understood. A single element is an isolated piece of information. Low element interactivity involves facts learned independently, like knowing an arrow key moves a cursor. Moving a cursor between coordinates is more complex. For novices, this involves 9 distinct interacting elements. The learner reads the horizontal and vertical axes for the current position, then identifies the goal coordinates on both axes. They must locate the intersection point and calculate the numerical difference between the current and goal horizontal positions. They then press the corresponding keys, calculate the vertical difference, and press the final keys to complete the move. These 9 steps rely on each other. The learner cannot complete the final step without simultaneously holding the previous coordinates and calculations in mind. Structural complexity depends on how many simultaneous connections a learner must maintain between individual facts. Researchers John Sweller and Paul Chandler tested this by studying split attention. They compared students using a computer alongside a separate manual against those using a manual with diagrams and text integrated on a single page. The experiment tested these two formats against both low interactivity and high interactivity tasks. To measure cognitive load, researchers added a secondary task. Learners had to recall letters triggered by an audio tone while studying the manuals. During low interactivity tasks, students using the separate manual and computer performed just as well on the tone test as those using the integrated manual. The simple tasks left enough working memory available to handle both the poor instructional design and the audio test at the same time. When students tried the 9-step coordinate task with the separate manual, their performance on the secondary tone test plummeted. Extraneous load from poor design remains manageable until the task's inherent interactivity consumes the remaining working memory capacity. Working memory processes visual and auditory information through separate channels. High interactivity often requires using both to avoid overload. In low interactivity tasks, like learning electrical symbols, printed text and visual symbols both fit within the visual channel's limits. For complex tasks like testing insulation resistance, using a wiring diagram and dense printed text simultaneously can overflow the visual channel. Converting the text into spoken narration distributes the load across both channels, keeping the total processing within working memory limits. Element interactivity is not a permanent value. It changes based on the learner's existing knowledge. In studies of relay circuits, instructional methods that helped novices were actually less effective for experts. This is known as the expertise reversal effect. This happens because of schema formation. A novice sees a circuit as several interacting components that must be held in mind at once. Through experience, the brain chunks these interacting elements into a single cohesive schema. The schema acts as a single element in working memory. What was once a high interactivity task is now low interactivity for that expert. Element interactivity decreases as schemas compress complex information into manageable units. Most cognitive load strategies, like integrating text and diagrams, only show benefits when the material has a high intrinsic load. To apply these principles, designers must first audit the element interactivity of the lesson. If interactivity is low, such as memorizing vocabulary, changing the format provides very little benefit to the learner. If the task requires high simultaneous processing, The next step is to evaluate the learner's expertise. For experts with existing schemas, formatting is less critical. For novices, reducing extraneous load is necessary to prevent overload. Working memory can only process a specific amount of data at once. Effective instructional design begins with a mechanical diagnosis of the interactivity within the subject matter itself.